Hello students, this session is on induction motors and myself, Bharat Vaike, Assistant Professor in the Department of Electrical and Electronics, Malnad College of Engineering. So let us begin with three-phase induction motors. Three-phase induction motors are widely used in the industries because of their advantages such as low cost, simple and robust construction, highly reliable and efficient operation, and low maintenance required. So induction motors are quite different compared to the DC motors because there will be no electrical connection from the rotor winding to any supply. The necessary voltage and current in the rotor required for proper operation are produced by induction from the stator winding. So that is why it is called as an induction motor. The operation of an induction motor is similar to that of a transformer. Both of these machines operate on the principle of mutual induction. So that's why induction motors are also referred to as rotating transformers. So in spite of all this, there are certain disadvantages, like the speed of the induction motors cannot be varied so easily. With the increase in the load, the speed drastically reduces. And compared to DC motors, the starting torque of induction motors is quite low. So next comes the classification of three-phase induction motors. So based on the construction of the rotor, three-phase induction motors can be classified into two types: squirrel cage induction motors and slip ring induction motors. So in squirrel cage induction motors, the structure of the rotor resembles a squirrel cage, and they are used in applications which require constant speed, moderate starting torque, low maintenance, for example, centrifugal pumps, fans, blowers, etc. The slip ring induction motors are also called as wound rotor or phase wound induction motors because the rotor is wound with a three-phase winding. So these type of motors are used in applications which require high starting torque, smooth acceleration, and adjustable speed. For example, traction, elevators, lifts, hoists, and cranes, etc. With respect to the construction of induction motors, a three-phase induction motor essentially consists of a stator and a rotor. For the construction of stator, high permeability silicon steel is used to reduce hysteresis loss, and the core is made up of thin silicon steel laminations or stampings which are insulated from one another by varnish to reduce eddy current loss. A small air gap is maintained between the stator and rotor, which is in the order of 1 mm, to make the air gap reluctance minimum. Reluctance is the opposition to the flux. For the stator winding, the copper coils insulated with enamel are used. A three-phase stator winding, which is wound for a certain number of poles, is placed in the slots present in the inner periphery of the core. The construction of stator is common for both squirrel cage and slip ring induction motors. Only the construction of rotor will be different. The rotor core of a squirrel cage induction motor is made up of laminations, and the slots are cut on the outer periphery of the core. So these slots are not in parallel with the shaft, but they are skewed. The conductors are heavy bars of copper or aluminum, which are placed in these slots, and they are insulated from the core. At each end of the rotor, the conductors are welded into two short-circuiting copper or aluminum end rings. The rotor conductors with end rings form a closed circuit which resembles a squirrel cage. So that's why the name. So squirrel cage induction motors are very strong and rugged in construction. So that's why in the 90% of the industrial applications where the induction motors have to be used, so squirrel cage induction motors are normally preferred there. In case of a slip ring induction motor, the rotor slots are wound with three-phase star-connected winding consisting of copper coils, which are wound for the same number of poles as that of the stator. The other ends of the winding are connected to three slip rings, which are situated at one end of the rotor shaft. These slip rings are made of phosphor bronze alloy. Three carbon brushes slide over the slip rings, which carry the current to and from the rotor windings. During starting, some external resistance is included in the rotor circuit, which provides high starting torque. As the rotor picks up the speed, the resistance is gradually cut out, and when the rotor reaches normal running condition, the slip rings are short circuited using a metal collar. Otherwise, the external resistance will cause rotor copper losses. Here you can see the exploded view of a squirrel cage induction motor. So these are the various parts. Similarly, you can see the exploded view of a slip ring induction motor along with its various parts. A three-phase induction motor is self-starting in nature. This is because of the principle of rotating magnetic field. The three-phase stator windings of an induction motor, let's call them as R, Y, and B, are phase displaced by 120 degrees electrical. When a three-phase supply is connected to the stator windings, the alternating currents flow through the three-phase windings of the motor. The current in each phase establishes its own flux. Therefore, the flux produced in phase R is given by phi m sin omega t. The flux produced by phase B is given by phi m sin omega t minus 120 degree. The flux produced by phase B is given by phi m sin omega t plus 120 degree. Therefore, the resultant flux at any particular instant is given by the vector sum of these three fluxes. So now we will consider the values of the resultant flux at four particular intervals 0, 1, 2 and 3, which are displaced by 60 degree from one another, where at interval 0 omega t is equal to 0 degree, at 1 omega t is equal to 60 degree, at 2 omega t is equal to 120 degrees, and at interval 3 omega t is equal to 180 degrees. In the first case, at interval 0, omega t will be equal to 0 degrees. Therefore, by applying omega t is equal to 0 in these equations, we will get phi r is equal to 0, phi y is equal to minus root 3 by 2 into phi m, and phi b is equal to plus root 3 by 2 into phi m. So these are the three fluxes we get. So now these three fluxes have to be vectorially added so as to obtain the resultant flux. Here, phi r in this case will be equal to 0. Therefore, this vector will be absent. Phi y is equal to minus root 3 by 2 into phi m. So that's why we have to write phi y in the opposite direction. And phi b is equal to plus root 3 by 2 phi m. Therefore, the vector diagram will be like this. So now by applying parallelogram law, we will obtain the resultant flux as shown here. Therefore, the resultant flux obtained is 1.5 phi m. In the second case, at interval 1, omega t is equal to 60 degree. By substituting omega t is equal to 60 in these three equations, phi r will be equal to plus root 3 by 2 into phi m, phi y will be equal to minus root 3 by 2 into phi m, and phi b is equal to 0. Similar to that of the previous case, if we write the vector diagram and compute the resultant flux using parallelogram law, the resultant flux obtained is 1.5 phi m. In the third case, at instant 2, omega t will be equal to 120 degree. So now by substituting omega t is equal to 120 degree in these three equations, phi r will be equal to plus root 3 by 2 phi m, phi y will be equal to 0, and phi b will be equal to minus root 3 by 2 into phi m. By writing the vector diagram and applying parallelogram law, the resultant flux obtained is 1.5 phi m. In the fourth case, at instant 3, omega t will be equal to 180 degrees. By applying omega t is equal to 120 degree in these three equations, phi r will be equal to 0 again, phi y will be equal to plus root 3 by 2 into phi m, and phi b will be equal to minus root 3 by 2 into phi m. With this, the corresponding vector diagram is drawn, and by applying parallelogram law, the resultant flux obtained is equal to 1.5 phi m. Thus, we can come to the following conclusions. After each of the instants, the resultant flux has a magnitude of 1.5 phi m, and it appears to rotate in the clockwise direction through an angle of 60 degree from the previous instant. Therefore, as omega t varies from 0 to 360 degree, the resultant magnetic flux rotates with an angular velocity of omega and has a magnitude of 1.5 phi m. The rotating magnetic flux has a speed, which is also known as synchronous speed, is given by ns is equal to 120 f by p, where f is the frequency and p is the number of poles. To understand the principle of operation, we must know how an induction motor starts. When a three-phase AC supply is connected to the stator of a three-phase induction motor, a rotating magnetic field is established in its air gap, which rotates at synchronous speed. This rotating magnetic field cuts the rotor conductors, and as per Faraday's laws of electromagnetic induction, an EMF is induced in the stationary rotor conductors. The frequency of this induced EMF is same as that of the supply, and its magnitude is proportional to the relative velocity between the rotating magnetic field and the conductors. The direction of the induced EMF is given by Fleming's right-hand rule. This induced EMF sets up rotor currents, which according to Lenz's law should oppose the very cause of it. So that's why it opposes the relative velocity between the rotating magnetic field and the rotor conductors. And according to Fleming's right-hand rule, the rotor conductors are subjected to a force, and the rotor starts to rotate in the direction of the rotating magnetic field. So next comes slip and its significance. So as we know, the rotor follows the direction of the rotating magnetic field, and in actual practice, the rotor can never reach the synchronous speed. If it does so, the relative velocity between the rotor conductors and the rotating magnetic field would become zero. This means that there will be no induced rotor EMF or current. Therefore, there will be no torque to drive the rotor. Hence, the rotor speed is always less than the speed of the rotating magnetic field. The difference between the synchronous speed ns and rotor speed nr is called as slip. The value of slip depends on load basically, As the load increases, the rotor will slow down and the slip increases. The slip is expressed as a percentage of synchronous speed, that is ns minus nr divided by ns into 100. Practically, in an induction motor, the change in slip from no load to full load is normally 3 to 6%. That's it. Now, with respect to the frequency of rotor current, when the rotor is in standstill condition, the frequency of the rotor current is same as that of the supply frequency. But when the rotor starts rotating, the frequency of the rotor EMF or current reduces as the relative velocity between the rotor and the rotating magnetic field decreases. Therefore, the frequency of the rotor EMF or current varies with the speed of the rotor. That is, the frequency of the rotor EMF or current varies with slip. Now, considering a particular rotor speed nr, for which the frequency of the rotor current will be f prime, then the slip ns minus nr is equal to 120 f prime divided by p. We know that the synchronous speed is given by ns is equal to 120 f by p. By dividing the first equation by second, we have f prime divided by f is equal to ns minus nr divided by ns, that is equal to slip. Therefore, the frequency of the rotor current is given by slip times the supply frequency. So now we will solve a couple of numerical problems. In the first problem, a 3-phase 4-pole 400 volts 50 hertz induction motor runs with a speed of 1440. We have to calculate the slip at which it is running. So for that, we have to calculate the synchronous speed and the rotor speed. The equation for synchronous speed is given by ns is equal to 120 f by p. The frequency is 50 hertz. The number of poles is 4. Therefore, by substituting, we will get 1500 RPM. To obtain the equation for rotor speed, we have to consider this particular equation, and simplifying it with respect to nr, we will get nr is equal to ns into 1 minus s. The rotor speed is 1440 RPM. The synchronous speed is 1500 RPM into 1 minus s. Therefore, the slip obtained is 0.04, or in percentage, it is 4%. In the second numerical, the frequency of the EMF in the stator of a 3-phase 4-pole induction motor is 50 Hz. The frequency of rotor current at full load is 1.5 Hz. So now we have to calculate the full load slip and the speed at which the motor is running at full load. For this, first let us consider the equation for synchronous speed, where ns is equal to 120 f by p. The frequency is 50 Hz. The number of poles is 4. Therefore, the synchronous speed is 1500 RPM. To calculate slip, let us consider this equation, where the frequency of rotor current is equal to slip times the supply frequency. The frequency of rotor current is 1.5 Hz and the supply frequency is 50 Hz. Therefore, the slip is equal to 0.03, or 3%. To calculate the rotor speed, let us consider this equation, where nr is equal to ns into 1 minus s. ns is 1500 RPM. Slip is 0.03. Therefore, the rotor speed at full load is equal to 1455 RPM. So now we will discuss about single-phase induction motors. Single-phase induction motors are widely used in domestic applications. With respect to its construction, it has a single-phase winding on the stator and a squirrel cage rotor. Unlike 3-phase induction motors, single-phase induction motors are not self-starting, because when a single phase supply is connected to the motor, the stator winding does not produce a rotating magnetic field, but it produces a pulsating magnetic field which does not rotate in the air gap. Therefore, the generated positive and negative torques cancel each other and the motor doesn't start. The motor starts only when the rotor is rotated through by hand or by any other mechanical means. So an auxiliary winding or starting winding along with centrifugal switch is provided with the main stator winding exclusively for starting purpose. During starting, the fields produced by the starting winding and the running winding produce enough torque for the motor to start. Once the motor reaches 70 to 80% of its nominal speed, the centrifugal switch opens and disconnects the starting winding. Now coming to the classification of single phase induction motors. So basically there are three types: split phase single phase induction motors, capacitor start or capacitor run single phase induction motors, and shaded pole single phase induction motors. Split phase single phase induction motors are used in fans and blowers, centrifugal pumps, separators, washing machines, small machine tools, duplicating machines, and domestic refrigerators. Capacitor start and capacitor run single phase induction motors are used in applications such as fans and blowers, voltage regulators, water pumps, and refrigerators. In domestic water pumps, which are used to pump the water to the overhead tank, capacitor start single phase induction motors are normally used. Shaded pole single phase induction motors are used in applications such as small fans, toys, instruments, hair dryers, ventilators, and electric clocks. So that is all with regard to induction motors. Thank you.